During the Second World War, the island now officially called Kyoto, known to many from that era as Iwo Jima, was a name etched into history. Today, this small volcanic outpost in the Pacific, situated roughly 1,200 kilometers, about 746 miles, south of Tokyo, is writing a different chapter. The ground has stirred yet again, and with it, a new threat has risen from below. An eruption style born not only of molten rock, but of scalding water and explosive steam that can remodel the island in a matter of minutes. At the island's southern end, Mount Suribachi, a low, brooding stratovolcano that once provided a strategic vantage point, and the iconic scene of a flag raising, has become the backdrop to a fresh sequence of volcanic unrest. Kyoto is not merely a battlefield relic. It is one of the most active volcanic environments in Japan. The island perches along the Izu-Bonin-Mariana Arc, a chain of submarine and emergent volcanoes that trace the subduction of the Pacific Plate. For generations, residents and station personnel lived with the nuisances of a breathing volcano: subtle quakes, fetid fumaroles, hot soils that steamed after rain, and sulfur in the air. Recently, however, the tempo and texture of the activity have changed, pointing to a system rebuilding pressure, reorganizing pathways, and testing the limits of the rock that contains it. Just after dawn on September 2nd, a thunderous detonation broke the morning calm and echoed across the water. What might have been dismissed as a single burst revealed itself as a complex, multi-stage event. Instead of a solitary vent, 5 separate craters opened in a short span. Each crater told its own story about where pressure was highest, where fluids could escape, and which fractures had been pried open by rising heat. The culprit was not a true magmatic fountain at the surface, but a different, notoriously unpredictable style of eruption: phreatic blasts. In these events, hot magma at depth doesn't necessarily erupt, but it flashes shallow groundwater to steam. That water, in an instant, expands by a factor of more than 1,000, turning the subsurface into a boiler under extreme stress. If confining rocks fracture, the trapped steam tears upward, blasting out old sediments, ash, altered rock, and occasionally hot fragments ripped from magma that never quite made it to daylight. The 5 craters did not scatter randomly like buckshot. They aligned along pre-existing zones of weakness, geological seams etched into the island over many thousands of years. 3 erupted in near unison, as though triggered by the same pressure pulse, traveling up a hidden conduit network. 2 others tracked along a mapped fault, locally referenced as the Akiji/Asidi structure, revealing that much of the island's plumbing is governed by old breaks in the rock. Volcanic systems frequently exploit these weaknesses. Once a crack opens, it becomes the preferred path for fluids and heat, the way a river returns to its channel after a flood. Dimensions alone convey the violence of the blast sequence. The smallest crater measured on the order of 35 meters, about 115 feet across, while the largest yawed opened to nearly 150 meters, close to 492 feet in diameter. A span that could swallow a football field with room to spare. Carving cavities like this requires an astonishing release of energy, comparable to detonating large stores of explosives underground. And yet the most striking detail may be what some of the craters threw out. Not only shattered clay, sand, and hydrothermally altered rock, but also incandescent bits of lava. Those glowing fragments imply magma lay very shallow, perhaps only a few tens of meters beneath the surface, close enough for the blast to rip pieces from its skin. Observers reported, or in some cases inferred from deposits, brief low run-out pyroclastic surges, hot turbulent clouds of ash and gas that skim along the ground at racing speeds. These were limited in extent, but their possible presence elevates the hazard profile beyond a simple steam burst, suggesting a complex interplay of heat, gas, and fragmented material. By the end of the episode, roughly 192,000 square meters, about 474,000 square feet, of terrain had been dusted and draped with new tephra. The island's map shifted yet again. Perhaps the most dramatic change was literal accretion of land. At the westernmost crater, so much debris was heaped outward that the shoreline advanced. Approximately 25,100 square meters, around 270,000 square feet of fresh surface, was added to the island's margin. On Ioto, growth is not a metaphor. It is a measurable expansion of real estate driven by eruptive power and sediment redistribution. A reminder that Earth's skin is perpetually under construction. For scientists, the craters are only the surface signature of a deeper process. A key diagnostic of that process is geodetic uplift, the island physically rising as magma and hydrothermal fluids pressurize the system below. During the first days of this sequence, precise instruments captured the ground lifting by about 10 centimeters, roughly 4 inches, per day. In the slow language of geology, that is a shout. Such rapid vertical motion implies substantial magma input or redistribution in shallow reservoirs. To make room for rising melt and superheated fluids, the brittle crust domes up like the lid of a pot under boil. Then a shift. The uplift pace slowed markedly. First, daily rise dropped by half. Then it halved again. Eventually, it settled near 0.5 centimeters, about 0.2 of an inch per day. To the casual reader, that might sound reassuring, a sign that the crisis has passed. Specialists are more cautious. A decline in uplift can mean depressurization after an eruption, but it can also indicate that fluids found new pathways, or that magma migrated laterally into a different pocket, or that gases are venting more efficiently through the newly opened fractures. In other words, the pressure did not necessarily vanish. It may have simply moved. From September 1st onward, cumulative uplift reached roughly 24 centimeters, about 9.4 inches, adding to years of steady rise. The long view is even more striking. The shoreline set during World War II now stands about 20 meters, around 66 feet, above present sea level. The beaches where soldiers once waded ashore are today perched high and dry, the ocean's old edge fossilized in terraces that step inland. This is the signature of a resurgent caldera system, a broad, subtle uplift caused by magma repeatedly refilling a large, shallow chamber and by hydrothermal fluids pressurizing overlying rock. Ioto is, in effect, the lid of a massive pressure cooker, and the cooker has been turned up for decades. Since around 2021, the island's restlessness has intensified. Minor eruptions and vigorous degassing have occurred with increasing frequency, each event a symptom of a deep engine that refuses to settle. Although the Volcanic Explosivity Index, VEI rating, assigned to the September episode is a modest one on a scale that tops out at 8, context matters. For this island in the 21st century, it is the largest event of its kind. Magnitude is not just about tall, incandescent fountains. It is also about how much the ground is rearranged, how rapidly the uplift accumulates, and how profoundly the subsurface plumbing is reconfigured. The operational consequences were immediate. Japan's self-defense forces postponed planned aircraft landing drills on Ioto and moved them to another site, an acknowledgement that even short run-out ash surges, ballistic ejections, or sudden ground deformation could endanger crews and equipment. Such decisions are never taken lightly. They reflect risk assessments that weigh the island's volatile temperament against the demands of training and logistics. Why are phreatic eruptions so unnerving? Unlike the classic lava-fed spectacle, they offer little warning. There may be subtle thermal changes, faint seismic tremor, or tiny bursts of gas composition shifts, but the trigger point can be abrupt. A blocked vent clears, a fracture tips open, groundwater flashes to steam, and an explosion follows. Depending on the geometry of the system and the permeability of the rocks, this can happen with minimal precursors that would be obvious to non-specialists. The resulting hazards include violent jets of rocks and ash, ballistics, short, fast-moving surges, and sudden collapse pits where overlying material has been evacuated. On a small island with critical infrastructure, any one of these can compel a rapid change of plans. The 5 new craters also provide scientists with a rare window into the volcano's inner pathways. Their positions and orientations illuminate the stress field, the directions in which rocks are being pulled apart or squeezed, and they reveal how pressurized fluids navigate the subsurface maze. The alignment along 2 principal trends points to an island-scale architecture. One set of fractures, likely tied to regional tectonics. The other controlled by the caldera's own geometry. When future episodes occur, these same alignments may reactivate, as fractured rock is easier to reopen than intact rock. Ejecta from the blasts, examined quickly in the field, included lava fragments tentatively identified as trachyte, a silica-rich composition that often forms when magma lingers in the crust, differentiating and evolving chemically. If confirmed, that would suggest a complex and potentially viscous magma system beneath the island, prone to trapping gases and developing overpressure. In such systems, the coupling between the magmatic and hydrothermal realms can be tight. Pulses of heat and volatiles from below can supercharge the steam-dominated layers above, priming them for phreatic bursts, even if the magma itself never breaches the surface. For now, the island continues to breathe. Small quakes tick by, fumaroles hiss, and the ground swells at a slower but still noteworthy pace. Whether the September sequence marks the crest of a cycle or the opening movement of a longer campaign is not yet clear. Both scenarios are plausible. Many caldera systems operate in pulses, with uplift accelerating, eruptive symptoms flaring, and then a tapering phase as the plumbing rearranges. Others ratchet forward in steps, each event creating new cracks and conduits that shorten the path from heat to water, thereby raising the odds of repeat blasts. What is unambiguous is the scale of change, already etched into the landscape. Craters dozens to hundreds of meters wide, a fresh apron of ash and debris, a measurable gain in land area, and a continuing elevation signal that leaves old coastlines stranded far inland. These are the footprints of a dynamic volcano. For those who study risk, the island presents a compact laboratory. Aviation operations, military logistics, and scientific fieldwork all must adapt to a terrain that can reconfigure itself between one survey and the next. Ioto's story is not simply about explosions, it is about balance. As magma rises, it must find room. As steam seeks escape, it seeks the path of least resistance. When those paths are clogged, pressure builds. When they open, pressure falls, sometimes catastrophically. The 5-crater eruption sequence captured that dance in miniature. A pressurized system sought outlets along familiar faults and newly weakened rock, bled off some of its energy in violent fashion, and in the process modified the very channels that will govern whatever comes next. The practical takeaway is caution without complacency. A falling uplift rate does not mean the hazard has ended. It means the system has changed state. New fractures may now be venting gas more efficiently. Alternatively, magma may have moved laterally, charging another section of the caldera's roof. Monitoring must stay continuous and multi-pronged. High-precision GPS and tilt meters to track surface motion, seismic arrays to listen for fluid movement and fracturing, gas sensors to catch shifts in sulfur dioxide or carbon dioxide that hint at magmatic pulses, and remote sensing to map thermal anomalies or shoreline changes after each event. For an island that once symbolized a pivotal human struggle, the present saga is a reminder that the deeper contest between heat from Earth's interior and the brittle shell that covers it never ends. Ioto has risen meters in a lifetime, carved new pits in an hour, and pushed out its shoreline in a single storm of ash and rock. Whether the next chapter brings more steam-driven violence, a lull, or a different style of eruption altogether, the island will keep telling its story in uplift lines, in crack patterns, and in the grain of fresh tephra that settles on its flanks. And for those watching, the lesson is the same as ever. The ground beneath us is not a static platform, but a living system, sometimes whispering, sometimes roaring, and always reshaping the world we think we know. Beneath the quiet farmlands and sleepy river towns of the American Midwest, something ancient is beginning to stir again. Over the past few months, scientists have logged more than 200 small earthquakes rumbling under the Mississippi River Valley, an area most Americans would never suspect hides one of the planet's most dangerous faults. The tremors are minor, too faint for anyone to notice without instruments, yet they're part of a pattern that tells a chilling story, one of strain and energy building deep below the surface, along a fracture zone capable of rewriting the map of the central United States. This isn't California, where cracks scar the landscape and mountain ranges mark the collision of tectonic plates. This is quiet farmland and bridges over muddy water, resting on top of one of Earth's most volatile scars. The New Madrid seismic zone doesn't give warnings. The last time it unleashed its fury, in the winter of 1811, the shaking was so intense that it made church bells ring in cities 1,000 miles away, and the tremors didn't stop for months. The first great quake struck at 2 a.m. on December 16, 1811, while the frontier slept. Entire homes were ripped from their foundations, forests collapsed, and the Mississippi River briefly reversed its flow. That was only the beginning. 2 more massive quakes followed, on January 23 and February 7, 1812, each stronger than the last. Eyewitnesses described the ground rolling in waves, the sky filled with a reddish haze, and new lakes forming overnight, including what we now know as Reelfoot Lake in Tennessee. The shaking toppled chimneys as far away as Cincinnati and was felt up into Canada. Now imagine that level of force in today's world. Highways cracking apart, power grids collapsing, Memphis plunged into darkness, and bridges around St. Louis twisting like wire. Scientists say the same fault lines that tore the land apart 2 centuries ago are still active and still locked with tension. Modern estimates suggest those 1811 to 1812 events reached magnitudes between 7.5 and 8.0. But unlike California, the dense bedrock of the eastern U.S. carries seismic waves far and wide, up to 5 times farther. A major quake here wouldn't devastate one city. It would rattle half the nation. Since the 1970s, more than 4,000 microquakes have quietly rippled through the New Madrid zone, each one a whisper from below, a reminder that the stress beneath our feet hasn't vanished. The landscape may look peaceful, but deep underground, fractures are once again beginning to groan. The same forces that split the continent eons ago are slowly reawakening, and that leaves geologists asking a question that's becoming impossible to ignore. When this fault moves again, will we be ready? The story of this region begins hundreds of millions of years ago when North America nearly tore itself apart. A massive rift, the Reelfoot Rift, began opening in what is now the Mississippi Valley, stretching from Arkansas toward Illinois. The continent never finished breaking, but the scar remained, a weak, fractured zone buried beneath layers of sediment. Over time, immense tectonic pressure squeezed the failed rift, slowly bending and stressing it until the crust gave way, as it did in 1811. Today, satellite GPS data show that the land here is subtly shifting again, millimeter by millimeter, as if the Earth itself is taking a deep breath before another violent exhale. When the next rupture happens, the effects could be catastrophic, because the soft rock of the Midwest transmits seismic energy so efficiently, shaking would spread across multiple states in seconds. A magnitude 7.7 quake in the New Madrid zone, according to FEMA simulations, would be felt from the Gulf of Mexico to the Great Lakes. Cities like Memphis, St. Louis, Little Rock, and even Indianapolis could experience severe shaking. Brick buildings, still common across the region, would crumble. Gas lines could rupture, igniting fires that spread through neighborhoods. The Mississippi's bridges, crucial to cross-state transport, could collapse or be rendered impassable. Within moments, cell towers would go down, roads would split open, and rescue operations would be trapped on both sides of the river. In St. Louis, the Gateway Arch might sway violently as downtown's historic riverfront shatters. Power stations near the river would automatically shut down. Hospitals would overflow. The shaking could last up to 4 endless minutes, long enough to turn calm into chaos. And that's before the aftershocks begin, thousands of them, some powerful enough to bring down whatever remains standing. FEMA's worst-case modeling predicts more than 80,000 people could be killed or injured, and over 2 million displaced from their homes. The financial toll could exceed $30 billion. possibly making it the most expensive natural disaster in U.S. history. Yet what makes this scenario even more alarming is how unprepared the region is. The Midwest has no major early warning network, few earthquake-resistant building codes, and almost no public readiness plans. While the West Coast invests billions in seismic infrastructure, the center of the country still sleeps on borrowed time. And it's not just the shaking itself that poses a danger. During the historic quakes of 1811 to 1812, witnesses described massive river tsunamis, waves surging through the Mississippi that overturned boats and sent the current flowing backward. If something similar occurred today, the damage would be unthinkable. The Mississippi is no longer a frontier river. It's lined with cities, ports, fuel depots, and power stations. Nearly 500 million tons of cargo move along it each year. A sudden inland surge could destroy bridges, rupture pipelines, and ignite fires across the water's surface. Then there's liquefaction, a phenomenon where shaking turns solid ground into quicksand. Entire neighborhoods could slide or sink, just as they did 2 centuries ago. And because the river system is a major artery for America's economy, a single catastrophic break in its infrastructure could paralyze supply chains across the country, halting fuel shipments, food distribution, and industrial transport. A new Madrid megaquake wouldn't just destroy cities. It could send shockwaves through the nation's economy and even global trade. The terrifying truth is that we're not ready. Thousands of schools, hospitals, and bridges across the Mississippi Valley were built with little or no seismic reinforcement. Many sit directly atop fault lines that have lain dormant for generations. The soils beneath them, soft, wet, and unstable, are primed to magnify the shaking when it finally arrives. Scientists monitoring the region know the strain is accumulating. The earth beneath the Midwest moves in silence, but silence has never meant safety. The last time the fault broke loose, it rearranged the land and made rivers flow in reverse. If it happens again, the outcome could rival the deadliest disasters in American history. And the worst part? It could happen tomorrow, or 50 years from now. There's no countdown clock, no clear warning. Only the uneasy knowledge that the heart of America sits atop a sleeping giant that is beginning, once again, to stir. So ask yourself, if the ground began to move beneath you right now, would your home withstand it? Would your city survive? These are questions no one in the Midwest wants to think about. But everyone should, because with the new Madrid fault, the question has never been if, it has always been when. It's starting to feel like mountains everywhere are loosening at the seams. If you've been tracking the recent run of rockfalls and slope failures, you're not alone. Share your take below on what this means for mountain belts and their valleys worldwide. Let's focus on one case study, Hawk Vogel, rising to roughly 8,500 feet, 2,592 meters. It stands apart in the eastern Algae Alps on the Bavaria-Tyrrell line, a solitary summit that dominates lower neighbors. Long before official records caught up in 1818, local shepherds were already on its ridges. Surveyors later used the peak as a triangulation point during early mapping efforts, proof of how prominent and reliable a landmark it once seemed. That appearance of permanence hides a touchy geology. Hawk Vogel is built mostly of Maine dolomite, a Triassic-age sedimentary rock. It's tough on the whole, but under the right stress, water, and temperature conditions, it can fracture and fail. History bears that out. On May 27, 1935, a massive failure ripped from the southwest face, sending thousands of cubic yards, thousands of cubic meters of rock downslope. More modest slips followed in 2005, 2007, and 2016. In other words, instability here isn't new. What's changed is the pace and scale of warning signs. The headline issued today is a summit-spanning crack that has been widening and deepening. Earlier measurements described a fissure about 130 feet, 40 meters long, approximately 10 feet, 3 meters wide, and approximately 26 feet, 8 meters deep. By 2024, high-resolution monitoring indicated dimensions on the order of 115 feet, 35 meters, in length, nearly 20 feet, 6 meters across, and roughly 20 feet, 6 meters deep. If a major section lets go, estimates suggest as much as approximately 340,000 cubic yards, approximately 260,000 cubic meters of rock could detach. Enough volume to reshape a valley floor and strip trails, alpine meadows, and infrastructure in its path. Since 2014, geoscientists and engineers, principally from the Technical University of Munich, and the GFZ Research Center in Potsdam have run an advanced warning network known as AlpSense Bench. Think of it as a digital nervous system for the mountain. Laser scanners, geophones, crack meters, GPS, and a continually updated 3D twin-track tiny movements down to hundredths of an inch, tenths of a millimeter. The system's goal isn't fortune-telling, it's pattern recognition. When motion accelerates in ways that typically precede failure, the instruments can flag danger a couple of days in advance. Like a weather forecast, it can detect trends and tipping behavior, but it cannot name the exact hour a block will break. Despite the warnings, curiosity draws people in. Hikers still edge toward the open fracture to see the problem up close. That uneasy mix, spectacle and risk, has turned Hochvogel from an icon of alpine beauty into a live hazard zone and one of the most closely watched mountains in the range. Seasonal conditions amplify the threat. As European summers warm, accelerated snowmelt and heavier rain load the rock mass with water. Rain infiltrates joints and bedding planes, acting like a lubricant, while also adding weight. Over the past 5 years, the crack's width has grown by about a foot, approximately 30 centimeters. A small number on paper, but alarming at this scale. The situation echoes a Swiss case near Blatten, where a slope's movement rate jumped from approximately 0.5 inch per day to approximately 0.5 inch per hour, an escalation that made collapse imminent. That is exactly the kind of acceleration the sensors here are tuned to catch. If a major release occurs, modeling suggests debris could surge into Austria's Hornbach Valley near the Germany border. Population in the direct path is sparse, but there are well-used trails, huts, and grazing areas. The consequences for those sites could be severe, even if towns farther away remain out of reach. To manage that risk, authorities have tightened early warning procedures so that rescue teams, alpine clubs, and local administrations on both sides of the frontier receive immediate alerts. With even 2 days' notice, priority areas could be cleared to prevent casualties. One event may not be the end of it. Specialists expect a stepwise breakdown is possible. Phases of failure spread over months or years. That kind of drawn-out destabilization would keep access limited and require continuous monitoring, with ripple effects for tourism and the local economy tied to mountaineering and hut networks. There's also the human layer. For communities that have lived with the mountain as a backdrop, a place of quiet and challenge, the present uncertainty carries a psychological toll. Trails that once felt routine now demand vigilance. The landscape itself feels provisional. Zooming out, Hochvogel's behavior fits a pattern seen across the Alps. In recent decades, extreme weather has become more frequent. Intense rain, hotter summers, and volatile storms. Lightning is under investigation too. Repeated electrical strikes can micro-damage rock, and when you combine that with prolonged saturation from rain, the structural integrity of fractured dolomite can degrade over time. It's death by 1,000 cuts. No single factor explains it, but together they tip the balance. Monitoring continues around the clock. Millimeters matter here. A slight jump in displacement speed can separate stable enough for now from failure in progress. And the hazard isn't only rockfall. Should a large collapse occur, secondary debris or mud flows could mobilize later, potentially traveling into the Hinterbach Valley and creating follow-on dangers. That's why planners are already sketching longer-term protections, not just emergency responses. Add it all up, climate trends, the natural fatigue of an old mountain, human exposure, and the slow arithmetic of geology. And Hochvogel has become a working laboratory. It's no longer just a summit to photograph or bag. It's a case study in how fast solid ground can change. The old cliché, solid as a rock, doesn't land the way it used to when the rock is riddled with widening joints and measurable motion. What does feel solid is the need to respect both the landscape and the science watching over it. If stories like this catch your interest, stick around, subscribe, tap the bell so you don't miss new deep dives, and pass this along to friends who follow natural hazards. And tell us in the comments what you make of the Hochvogel situation, or if you've seen similar slope instabilities on your own travels. Your experiences help widen the discussion. For those who want a little more technical context, consider the mechanics at play. Main dolomite typically features bedding parallel weaknesses and vertical fractures, formed over geologic time. Freeze-thaw cycles widen those voids as water expands into ice, and in warmer seasons, infiltrating rain reduces friction along those same plains. Add the occasional seismic vibration, regional earthquakes, or even distant tremors can contribute, and you have a system primed for episodic movement. Each episode need not be catastrophic on its own, but cumulatively, they can reduce the safety margin until a nudge, an intense storm, a temperature swing, or a saturated week pushes the mass beyond its threshold. That is where monitoring earns its reputation. Laser scanners map the face repeatedly, comparing point clouds to detect subtle bulges or overhang growth. Geophones listen for microcracking, tiny acoustic emissions that hint at bonds failing within the rock mass. Crack meters measure aperture changes across the fissure, while GPS monuments track surface displacement. Feed all that into a living 3D model, and you can see which blocks are moving coherently and which are locked, giving responders a target for closures and evacuations that is grounded in data rather than guesswork. The goal is not to eliminate risk, no one can, but to convert uncertainty into informed decisions that save time and lives. The social piece matters too. Messaging must balance clarity and proportion, neither downplay nor sensationalize. Local guides, HUD operators, and municipal leaders succeed when communications are simple, timely, and consistent. Close today signs need clear detours. Alert levels should be color-coded and explained. Evacuation drills should be practiced in shoulder seasons when routes are less crowded. Small choices like multilingual notices or QR codes linking to live dashboards can save minutes when minutes matter, and visitors can help by treating closures as lines not to be crossed rather than challenges to brag about online. Finally, remember that mountains change on human timescales more often than we think. The Alps are not static museum pieces. They're dynamic landforms shaped by uplift, weathering, ice, water, and gravity. Hochvogel is a reminder that beauty and hazard live side by side. Respect the forecasts, heed the ropes, and treat that widening crack not as a spectacle, but as a message from the rock itself. As we wrap up, a quick note on personal responsibility. If you visit this area, plan conservatively. Check current closures, register your route when required. Carry a map and headlamp even on fair weather days, and turn around early if the ground or the forecast feels wrong. The summit will be there tomorrow. Your margin for error may not.